Somewhere in the 1870s, a proof that everyone believed quietly stopped working, and almost nobody noticed. What broke was the explanation for why the past is different from the future. After it broke, the fossil record stopped being self-justifying evidence. Your memory of this morning stopped being a window and became a physical object with a price on it. And your confidence that a glass shatters rather than reassembles turned out to rest on an assumption that a Nobel laureate would later describe, on camera, as coming from outside the province of what we call physical laws. None of that was announced. It was published, argued over in 4 papers in a German journal, conceded, and filed under assumptions, where it has been sitting ever since. All of it traces back to one technical detail about colliding molecules, a detail that reads like a harmless simplification and has the entire direction of time hidden inside it. Tonight, that detail. A friendly objection raised in Vienna in 1876. A Nobel Prize won at Brookhaven for finding the wrong crack in time symmetry. A number Roger Penrose calculated that cannot be written down inside this universe. And a letter Ludwig Boltzmann sent to Nature in 1895 which, taken seriously, means you have probably never existed for longer than a few seconds. Settle in, because by the end of this you will not be able to experience your own memory as a plain record of the past. Fault Lines is one of the channels supported by Meridian Labs on Patreon. Members get every episode ad-free across all of them, plus early access before anything goes public. Subscribe or join if you have not. Let us start where it started. Take the equation that describes a planet moving around a star. Find the letter that stands for time. Replace it with minus itself so that time runs the other way, and solve the whole thing again. The equation does not object. It hands you back a perfectly legal orbit, running backwards, obeying every rule of physics exactly as written. Now do the same thing to Maxwell's equations, the 4 lines that govern every photon of light that has ever entered your eye. Same result. The backwards version is just as valid. Do it to Einstein's field equations, the ones that describe how mass bends space-time and how the universe expands. Same. Do it to the Schrodinger equation, the equation that governs the behaviour of every electron in every atom in your body. Same again. There is nothing in the fundamental laws of physics that tells you which way time runs. The direction is not written into the machinery. It is not a term in any equation, it is not a constant anyone has measured, and it does not appear anywhere in the description of how matter and energy actually behave. And yet, you have never once seen a dropped glass gather itself off a kitchen floor and reassemble on the counter, with the water back inside it. You have never seen smoke pour down a chimney and pack itself into unburned wood. You have never seen a bruise appear on your arm and then travel backwards into the corner of the table you walked into. Every single thing you have ever observed from the moment you were born has happened in exactly one direction, and the laws that govern all of it are completely indifferent to which direction that is. That gap is the largest unexplained hole in physics. Not the largest unsolved problem, because physics has plenty of those and most of them are honest admissions of ignorance. This is different. This is a case where the standard answer is taught in every thermodynamics course on Earth, appears in every popular science book, and is repeated by physicists at dinner parties, and the standard answer does not work. It has not worked since the 1870s. The people teaching it know it does not work. And almost nobody says so out loud, because saying so out loud requires admitting that one of the load-bearing assumptions of modern cosmology was bolted onto physics by hand, without derivation, without justification, because otherwise the equations would not describe the world you actually live in. The standard answer is entropy. You have heard it. Entropy always increases, disorder always goes up, the universe runs down, and that is why time has a direction. It is on t-shirts. Arthur Eddington, who coined the phrase time's arrow in 1928, wrote that the law of entropy holds what he called the supreme position among the laws of nature. He was not being modest about it. He argued that if your theory contradicts Maxwell, so much the worse for Maxwell, and if it contradicts observation, well, experimenters do occasionally make mistakes, but if your theory contradicts the second law of thermodynamics, there is nothing left for it but to collapse in deepest humiliation, and here is the part that should disturb you. The second law of thermodynamics has a completely different status from Maxwell's equations. It is a statistical statement about probability. It is not exact. It can be violated. It has been measured being violated in laboratories, and the argument that produces it is itself perfectly symmetric in time. Run the standard entropy argument forward, and it tells you that the future will be more disordered than the present. Run the exact same argument backwards, using the exact same logic, and it tells you that the past was more disordered than the present too. Think about what that means for a moment, because it is not a technicality. The statistical reasoning that everyone uses to explain why your coffee cools down also predicts, with equal force and equal confidence, that 5 minutes ago your coffee was hotter than it is now, only if you already assume that it was. Left to its own devices, the mathematics says the most likely history of a lukewarm cup of coffee is that it was lukewarm the whole time and briefly fluctuated. It says the most likely history of a half-melted ice cube is not a whole ice cube. It says the most likely history of the room you are sitting in is a room that has always looked roughly like this, with your memories being an accident. The second law does not explain the arrow of time. It has the arrow of time already inside it, smuggled in as an assumption about how things started, and the moment you go looking for where that assumption came from, physics goes quiet. I have spent an unreasonable amount of time reading the primary literature on this, the original papers in German from the 1870s and the modern cosmology papers from the last 5 years, and the thing that kept me up was not the difficulty of the problem at all. It was watching how openly the people who work on it admit that there is no answer, and how completely that admission fails to reach anyone outside the field. Richard Feynman said it plainly in a lecture theatre at Cornell in 1964 in front of an audience, on film. He said that in order to get the arrow of time out of physics, you have to add an extra hypothesis, an assumption that the universe in the past was more ordered than it is today. And he said that this statement comes from outside the province of what we ordinarily call physical laws. Outside the province of physical laws. That is a Nobel laureate telling a room full of people that the reason you can remember yesterday and not tomorrow is a postulate that had to be attached to physics from the outside, because physics could not generate it. What that postulate is, why the universe had to start in a state so astronomically improbable that the number describing its improbability cannot be written down inside this universe, and what happens to your sense of your own past when you follow that logic all the way down, is where this is going. But the route runs through a graveyard in Vienna, through a 1964 experiment at Brookhaven that won a Nobel Prize and turned out to be irrelevant, and through a suggestion made by a physicist in 1895 that, if it is correct, means you have almost certainly never existed for longer than a few seconds. That last one is entirely serious. It is a live problem in theoretical cosmology. It has its own literature, and serious people have written papers arguing about whether it makes the entire enterprise of doing science self-defeating. We will get there. But this story does not start with cosmology. It starts with a friendly argument between two men who worked in the same building in Vienna, one of whom pointed out, politely, that his colleague had just proved something impossible. Ludwig Boltzmann was born in Vienna on the 20th of February, 1844, the eldest son of a tax official who died of tuberculosis when Ludwig was still a teenager. He took his doctorate at the University of Vienna in 1866 under Josef Stefan, and then spent the next 4 decades moving between Graz, Vienna, Munich, Leipzig, and Vienna again. A restless academic career that reads, in the biographies, like a man who could never quite settle anywhere for long. His students included Svante Arrhenius and Walther Nernst, both of whom would go on to win Nobel Prizes. He never won one himself. What Boltzmann was trying to do was one of the most ambitious projects in the history of science, and it is worth being precise about it, because the ambition is what makes the failure interesting. Thermodynamics in the 1860s was a set of empirical rules. Heat flows from hot to cold. Engines cannot be perfectly efficient. Rudolf Clausius had given the second of these rules a quantity in 1865, in a paper in Annalen der Physik, and he named that quantity entropy. He built the word deliberately from the Greek word for transformation, and he said so explicitly in the paper. He wanted it to sound as close as possible to the word energy, because he thought the two quantities were so closely related in their physical meaning that a similarity in the naming seemed appropriate. That was a description, not an explanation. Clausius could tell you that entropy increases. He could not tell you why. The why was supposed to come from atoms. Boltzmann's project was to show that all of thermodynamics, including the one-way flow of heat, could be derived from nothing but atoms bouncing off each other according to Newton's laws. If he could do that, thermodynamics would stop being a set of observed regularities and become a consequence of mechanics. The universe would not need a separate rule saying heat flows one way, it would just fall out of the collisions. In 1872 he published the paper that appeared to do it. The title translates as Further Studies on the Thermal Equilibrium of Gas Molecules, and it ran to nearly 100 pages in the Proceedings of the Vienna Academy. In it he defined a quantity, which later got the label H, that described how far a gas was from equilibrium, and then he proved, from the mechanics of colliding molecules, that H can only decrease. It goes down and it never goes back up. Since entropy is essentially the negative of H, this meant entropy can only increase. The second law of thermodynamics derived from Newton. It was one of the most celebrated results of 19th century physics. It also could not possibly be true, and the man who explained why worked down the corridor. Josef Loschmidt was 23 years older than Boltzmann, and by any reasonable measure he had had a much harder road into science. He was born in 1821 in a village in northern Bohemia to a peasant family, and reached education at all only because a local priest noticed he was unusually bright and arranged for him to be schooled. He spent years working in industrial chemistry before finding his way back into academic physics in middle age. In 1865 he did the calculation that made his name, producing the first credible estimate of the size of an air molecule and therefore of how many molecules sit in a given volume of gas. The number density of an ideal gas is still called the Loschmidt constant. He and Boltzmann were colleagues at Vienna, and by every account, friends which matters. Because what Loschmidt did to the H theorem in 1876 was never an attack. He asked a question, politely, and the question was devastating. Loschmidt pointed out something that anyone can verify in an afternoon with a pen. Newton's laws are reversible. If you have a gas of molecules flying around and colliding, and at some moment you reach in and reverse the velocity of every single molecule, leaving their positions exactly where they are, the resulting motion is also a perfectly valid solution to Newton's laws. Every collision runs the other way, and every trajectory retraces itself. The gas unmixes. The entropy goes down. Therefore, Loschmidt said, for every possible history in which H decreases, there exists a corresponding history in which H increases, and it is exactly as legal mechanically. you cannot derive an irreversible result from reversible ingredients. Something else got into the proof. The objection has a German name, the Umkehreinwand, which translates as the reversibility objection, and it is one of the cleanest kills in the history of theoretical physics. Boltzmann had claimed to squeeze a one-way process out of a two-way machine. Loschmidt showed the machine had no preference at all. There is a story, passed down through the physicist Mark Kack, that Boltzmann's response to the velocity reversal argument was to tell Loschmidt to go ahead and reverse them. I have never been able to trace that line to a primary source, and I would treat it as an anecdote rather than a quotation, but the sentiment is real because Boltzmann's actual published response amounted to something close to it, and the actual response is far more interesting than the joke. What Loschmidt had exposed was a specific assumption buried in the 1872 derivation. To make the mathematics work, Boltzmann had assumed that the velocities of two molecules about to collide are uncorrelated. In German it is the Stoßschalandsatz, the collision number assumption, and it is usually translated as molecular chaos. It sounds innocent. It is not. Assuming that molecules are uncorrelated before they collide, but not after, is itself a statement about the direction of time. Collisions create correlations. Two molecules that have just bounced off each other carry information about each other in their velocities. If you assume that this correlation is absent going into a collision and present coming out, you have already decided which way time runs, and you have decided it before you have proved anything. The asymmetry in the conclusion was in the premises the whole time. I want to stop here and make sure the weight of this lands, because it is the load-bearing failure and everything downstream inherits it. Boltzmann did not derive the arrow of time from mechanics. He inserted the arrow of time into the mechanics in a technical assumption about collision statistics that looks like a harmless simplification, and then recovered it at the other end and called it a proof. It was not fraud, and it was not incompetence. He genuinely did not see it, and neither did anyone else for 4 years, which tells you how well hidden the assumption was. But Loschmidt's objection was only the first one, and it was the gentler of the two. 20 years after Loschmidt, a 25-year-old mathematician named Ernst Zermelo, working as assistant to Max Planck in Berlin, delivered the second one. And where Loschmidt had asked a friendly question, Zermelo was going for the throat. Zermelo's weapon came from Henri Poincaré. In 1890, in a long paper in Acta Mathematica on the three-body problem, Poincaré had proved a theorem about bounded mechanical systems. If a system has finite energy and is confined to a finite region, then almost every state it can be in will eventually recur. This is not approximate recurrence in some loose sense. The system returns arbitrarily close to any state it has previously occupied, and it does so infinitely many times, given infinite time. Zermelo took that theorem and pointed it at the H theorem in a paper in Annalen der Physik in 1896. If Poincaré is right, he argued, then H cannot decrease forever. A gas in a box is a bounded mechanical system. It must eventually return close to its starting configuration, which means H must eventually go back up. A quantity that is guaranteed to return to its initial value cannot be a quantity that only ever decreases. The H theorem had gone from unproved to incompatible with mechanics. Boltzmann replied that same year in a paper whose title translates as Reply to the Thermodynamic Considerations of Mr. Zermelo. Zermelo responded. Boltzmann responded again in 1897. 4 papers, 2 men, 1 journal, and by the end of it thermodynamics was a different subject. Boltzmann's defense was the recurrence times. He conceded that Poincaré recurrence is real. He then argued that for any gas you could actually put in a box, the time you would have to wait is so long that the objection has no physical content. Take a small volume of ordinary air, the amount that fits in a thimble, and ask how long you would wait for its molecules to return to a given arrangement. The answer is a number with more zeros in it than the observable universe has atoms. The universe is roughly 14 billion years old. The recurrence time is not 14 billion years, or 14 trillion, or any number that stands in a comprehensible relationship to 14 billion. It is a number that requires exponent towers to write. Boltzmann's point was that a theorem which becomes relevant only after that much time is a mathematical curiosity, not a physical objection. He was right about the timescales. He lost the argument anyway, and he lost it in a way that is usually left out of the retelling. Here is the version you will find in most popular accounts. Boltzmann versus Zermelo, atomism versus the anti-atomists, and Boltzmann wins because atoms turned out to be real and Zermelo was on the wrong side of history. That framing is closer to backwards than it is to simplified. The historian of physics Josef Loschmidt, writing in the introductory notes to Zermelo's collected works, put it about as bluntly as an academic gets. He wrote that in the popular telling Boltzmann has the upper hand, but that in fact Zermelo had the better arguments in the debate, that Zermelo's objections were stated fairly and precisely, and that Boltzmann's responses failed to answer or fully clarify his own position. Boltzmann was right about atoms, and wrong about the logic. Both of those things are true at once, and only one of them gets taught. Because what Boltzmann actually conceded over the course of those 4 papers was the entire original project. He had set out in 1872 to derive the second law from mechanics. By 1897 he was arguing that the second law is a statistical statement which is true for practical purposes over human timescales, that entropy decreases are possible and merely fantastically improbable, and that the reason we observe a one-way flow is something to do with the particular state our region of the universe happens to be in. What he had arrived at by then was the abandonment of the attempt to prove the second law, dressed as a defense of it. And the cost of the concession is enormous, in a way that took another century to properly digest. Once you admit that the second law is statistical rather than mechanical, the argument for entropy increase becomes a probability argument. Probability arguments do not have a preferred direction of time. They are about counting configurations, and counting configurations is a completely timed symmetric activity. Follow that through, take a box of gas, all of it crammed into one corner, and ask what it does next. The overwhelming majority of possible future evolutions spread it out, because there are vastly more spread out configurations than corner configurations. That is the standard argument, and it is correct. Now take the same box in the same crammed state and ask what happened before. Apply the same counting. The overwhelming majority of possible past histories that lead to a crammed corner are histories in which the gas was spread out and randomly fluctuated into the corner, because, again, there are vastly more spread out configurations than corner ones. The statistics do not care which way you are looking. They say the gas was probably spread out a minute ago and will probably be spread out a minute from now, and that its current low entropy state is a fluctuation between 2 ordinary ones. Which is wrong. Obviously, flagrantly wrong, about every real system you have ever encountered. When you find an ice cube half melted in a glass, the water did not spontaneously fluctuate into an ice cube. There was an ice cube, and it has been melting. You know this. Everyone knows this. And the statistical mechanics that supposedly underwrites the second law of thermodynamics gets it backwards every single time you point it at the past. Physicists have a name for the extra ingredient you have to add to stop this from happening. We will get to the name, and to the man who coined it, and to the reason that naming it did not solve anything. But I want to be precise first about how bad the situation is, because there is a temptation to hear all this as philosophical hair-splitting. This is the difference between a theory that predicts the world and a theory that has to be told about the world in advance. Statistical mechanics, applied honestly and symmetrically, predicts that your memories are false, that the historical record is a coincidence, that the fossils in the ground assembled themselves out of noise, and that every photograph you have ever seen is a statistical accident. It predicts this with overwhelming confidence. The only thing stopping it is a hand-inserted assumption about the state of the universe roughly 14 billion years ago. Boltzmann understood this by the 1890s. He said so, in print, in English, in a letter to Nature. What he proposed as the solution is where this stops being a story about gases in boxes and becomes a story about you. The letter appeared in Nature on the 28th of February, 1895, under the title On Certain Questions of the Theory of Gases. It is short. Boltzmann is mostly defending his kinetic theory against British critics. And then, at the very end, almost as an afterthought, he introduces an idea that he explicitly does not claim as his own. His words, verbatim, "I will conclude this paper with an idea of my old assistant, Dr. Schetz. We assume that the whole universe is, and rests forever, in thermal equilibrium. The probability that one, only one, part of the universe is in a certain state is the smaller the further this state is from thermal equilibrium, but this probability is greater, the greater is the universe itself." Ignaz Robert Schwetz was a research assistant. That is essentially all that survives of him in the physics literature. His idea, delivered second-hand by his employer in a short letter to a British journal, is one of the most consequential proposals anyone has ever made about the nature of time, and it is still generating papers 130 years later. What Schetz and Boltzmann were suggesting is this. Perhaps the universe as a whole is already at maximum entropy. Perhaps it has been sitting there, dead and uniform, for an eternity, and will continue to sit there for an eternity more. In an infinite amount of time, random fluctuations will occasionally produce local regions of lower entropy, the way a gas at equilibrium will occasionally. By chance, have all its molecules in one half of the container for a moment. The bigger the fluctuation, the rarer it is. But over infinite time, arbitrarily large fluctuations happen arbitrarily often, and in one of those fluctuations, sitting on the slope where entropy is climbing back toward equilibrium, are we. What we call the direction of time is nothing but the direction in which our particular fluctuation happens to be relaxing. Boltzmann went further in his later writing and drew the conclusion that follows. In other regions of the universe, on the other side of other fluctuations, the arrow of time would point the opposite way, and the inhabitants of those regions, if there were any, would call their direction the future, exactly as we do, and neither of us would be wrong, because the distinction is local. Up and down are not features of space, they are features of standing on a planet. Past and future, on this proposal, are not features of time, they are features of standing on a slope. I find this genuinely disorienting every time I read it, and I want to be honest that I do not know how to think about it even now. It is the first serious attempt to explain the arrow of time rather than assume it. It is elegant. It requires no special initial conditions, no unexplained beginning, no bolted-on postulate, because it dispenses with the beginning entirely. And it is, as far as anyone can tell, catastrophically self-destroying in a way that Boltzmann did not live to see worked out. That last sentence is doing a lot of work. Hold on to it. It comes back, and when it does it, will not be a curiosity about gases. Boltzmann had 11 years left to live when that letter went to press. He was fighting on two fronts by then. The scientific front was the arrow of time, which he had not solved, and knew he had not solved. The other front was atoms themselves, and it is worth understanding how exposed his position was, because the standard story about this is also wrong in a specific way that matters. The dominant opposition came from a school called energeticism, whose most prominent figures were Wilhelm Ostwald and Ernst Mach. Their position came out of a rigorous philosophical stance about what physics is allowed to talk about. Mach in particular held that science should confine itself to relations between observable quantities, and in 1895 nobody had observed an atom. Atoms were an inference, a modelling convenience, a hypothetical bookkeeping device that happened to make gas calculations come out right. Building the whole edifice of thermodynamics on entities nobody had seen struck Mach as a category error. There is a famous line attributed to him, delivered as a challenge to atomists, asking whether they had ever seen one. I cannot find a reliable primary source for that phrasing, and you should treat it as probably apocryphal. The underlying position is well documented regardless. Simon Schaffer, writing about Carlo Cicognani's biography of Boltzmann, described him as a kind of deceived lover, a man who had devoted himself entirely to atomic theory and whose colleagues could not follow him. That is the emotional shape of the last decade of his life. He was defending a picture of matter that turned out to be completely correct in front of an audience that regarded it as metaphysics, while simultaneously knowing that the crown jewel of that picture, the derivation of the second law, had a hole in it he could not close. Now hold that image and step forward 70 years, because the next serious candidate for an explanation of the arrow of time did not come from thermodynamics at all. It came from a basement laboratory on Long Island, it involved a particle that nobody outside nuclear physics had heard of, and it won a Nobel Prize for demonstrating that the laws of nature are not, in fact, perfectly symmetric under time reversal, which sounds like exactly the answer everybody had been waiting for. It is not, and the reason it is not is one of the most instructive dead ends in modern physics. In 1964, at Brookhaven National Laboratory on Long Island, 4 physicists set out to do a piece of routine confirmation. James Christiansen, James Cronin, Val Fitch, and René Turley were studying neutral kaons, a species of unstable particle produced in accelerator collisions, and they expected to confirm something everyone already believed. To understand why the result mattered, you need 3 letters. C stands for charge conjugation, the operation of swapping every particle for its antiparticle. P stands for parity, the operation of reflecting space, turning left into right. T stands for time reversal, running the film backwards. Physicists had already had one nasty shock in this area. Parity, P on its own, had been shown to be violated by the weak nuclear force in 1956, which was a genuine scandal at the time because the symmetry between left and right had seemed like a self-evident feature of a sane universe. The retreat position was that C and P together, the combination, remained exact. Swap the particles for antiparticles and reflect space at the same time, and the laws would be identical. Christiansen, Cronin, Fitch and Turley found that they were not. The long-lived neutral kaon, which by the rules of combined charge and parity symmetry should decay into 3 pions and never into 2, was decaying into 2 pions. It happened rarely, roughly 1 time in 500. The paper, Evidence for the 2-pi Decay of the K20 meson, appeared in Physical Review Letters on the 27th of July, 1964, Volume 13, page 138. The entire result rested on a handful of events. Going back through the notebooks, the count in the run designed to test charge and parity invariance was about 45 events, with an uncertainty of around 10. 45 events. That is the whole thing. Cronin and Fitch received the Nobel Prize in Physics in 1980 for it. Here is why it matters for time. There is a theorem proved in the 1950s called the Cepheid theorem, which says that the combined operation of charge conjugation, parity, and time reversal, all 3 applied together, is an exact symmetry of any local quantum field theory that respects special relativity. Julian Schwinger had it implicitly in 1951. Gerhard Luders and Wolfgang Pauli published explicit proofs in 1954 and 1955, which is why it is sometimes called the Luders-Pauli theorem. John Stuart Bell, then a young physicist at Birmingham, proved it independently around the same time. Res Yost gave the fully general version in 1958, tying it directly to the structure of Lorentz invariance. The CPT theorem is about as close to sacred as anything in particle physics gets. It is why we know antimatter has exactly the same mass as matter, and it has an immediate consequence. If the combination of all three symmetries is exact, and the combination of the first two is broken, then the third one must be broken too, in precisely the compensating amount. Charge and parity violation implies time reversal violation. Necessarily, automatically, which means that as of 1964, physics had a genuine, experimentally verified, Nobel-decorated instance of nature distinguishing between forward and backward in time. The direct measurements came later, and they are worth naming because the precision is remarkable. At CERN in 1998, the C-Plear collaboration measured a difference in rate between neutral kaons turning into their antiparticles and the reverse process, reporting an asymmetry of 6.6 thousandths, with a statistical uncertainty of 1.3 thousandths and a systematic uncertainty of 1.0 thousandths. Whether that counted as truly direct time reversal violation was argued about, because the measurement involves decay, and decay is irreversible for boring reasons that have nothing to do with the symmetry in question. The clean result came from the Baybar experiment at the Stanford Linear Accelerator Center. In 2012, using 468 million pairs of B mesons produced in electron-positron collisions, the collaboration observed time reversal violation directly by comparing processes with their initial and final states exchanged. The paper is in Physical Review Letters, Volume 109, Article 211801. The statistical significance was 14 sigma. For context, particle physicists call 5 sigma a discovery. 14 sigma is not a result anybody argues about. The laws of physics, then, are not perfectly time-symmetric. That is confirmed. That is real. And it explains absolutely nothing about why your coffee cools. This is the step where the reasoning breaks, and a lot of otherwise well-informed people miss it, and it is worth being blunt about, because the error is seductive. The reasoning goes, the arrow of time is a mystery, physics is time-symmetric. Oh, look, here is a place where physics is not time-symmetric. Mystery solved. Every step of that is defensible except the last one, and the last one is a complete non sequitur. Sean Carroll wrote about this in November 2012, just after the Baybar result, in a post whose title was simply that time reversal violation is not the arrow of time. His argument is precise, and I want to give it to you in his own words rather than paraphrase it into mush. He wrote that it is not a matter of the size of the effect, that particle physics, no matter how big the time reversal violation is completely reversible, that the arrow of time is all about irreversibility, and that there are not any B mesons or kaons playing a crucial role in what happens when you scramble eggs. Read that again, because there are 2 separate points in it, and both are lethal. The first is the reversibility point. Charge and parity violation does not make particle physics irreversible. The dynamics remain unitary, which means information is conserved and every process can in principle be run backwards. Time reversal violation means the backwards process happens at a slightly different rate. Not that it cannot happen. A universe with charge and parity violation is still a universe in which every microscopic process is invertible. Irreversibility, the thing you actually experience, the thing that means eggs do not unscramble, is a different animal entirely. The second point is the domain point. The effect is confined to the weak nuclear force acting on a handful of exotic particle species. Kaons and B mesons are produced in accelerators and in cosmic ray showers. They last for fractions of a microsecond, and they are involved in exactly none of the processes that constitute your daily experience of time passing. Your coffee cooling is electromagnetic and thermal. The scrambling of an egg is chemistry. Your memory of yesterday is electrochemical. Not one of those processes cares whether the weak force treats matter and antimatter identically. There is a serious version of the claim, and it deserves acknowledgement rather than dismissal. Charge and parity violation is thought to be necessary for the matter-antimatter asymmetry of the universe. The reason there is something rather than nothing in the way of ordinary matter, and you do need matter around before you can have a thermodynamic arrow to talk about. But that is a story about what exists, not about which direction processes run. The asymmetry that made the matter is not the asymmetry that makes it flow. 4 physicists at Brookhaven found a genuine crack in the time symmetry of natural law, and it turned out to be the wrong crack, which is the pattern of this entire subject, and the pattern is about to repeat, because the next candidate answer is even more popular, even more confidently asserted, and even less relevant. If you ask a room of educated non-physicists what modern physics says about time, a good fraction will tell you something about relativity. Time is the 4th dimension. Time is relative. Time slows down when you move fast. Past, present and future are all equally real, and the sense that time flows is a psychological illusion, and they will usually reach, at some point, for a line of Einstein's. The line is real, and it is worth getting right, because it is one of the most abused quotations in the history of science. Michel Besso was Einstein's closest friend. They met in Zurich in the 1890s, they worked together at the patent office in Bern, and Besso is the only person thanked by name in the 1905 paper on special relativity. Besso died in March 1955. Einstein, then 76 and with weeks left to live himself, wrote to the family. The letter is dated the 21st of March 1955, and it is catalogued in the Einstein archives. What he wrote was that Besso had departed from this strange world a little ahead of him, that this means nothing, and that people like them. Who believe in physics know that the distinction between past, present and future is only a stubbornly persistent illusion. A month later, Einstein was dead. That sentence has been carried into 1,000 books and videos as Einstein's verdict on the nature of time. And I want to be careful here, because there is a version of the argument that is legitimate physics, and a version that is over-reading a condolence letter written by a dying man to the family of his oldest friend. The legitimate physics is this. In special relativity, simultaneity is relative. 2 events that are simultaneous in your reference frame are not simultaneous in the frame of someone moving relative to you. There is no universal now, and if there is no universal now, then the idea of a moving present moment, a spotlight of nowness sweeping through history, does not have a well-defined meaning. This leads naturally to what philosophers call the block universe, in which the whole of space-time, all events at all times, simply exists, and your experience of moving through it is a feature of you rather than of the universe. Tim Maudlin, a philosopher of physics at New York University, has spent years arguing that this inference is far weaker than it is usually presented as being, and that Einstein did not actually think time is an illusion in the sense the quotation is used to support. His position is that relativity constrains how the passage of time works without demonstrating that it does not happen, and that treating the direction of time as fundamental and primitive, a basic feature of the world rather than something to be derived from entropy, is a defensible and arguably superior position. I think his argument deserves more attention than it gets, and I will come back to it, because it is the strongest available response to everything else in this story. But notice what has happened even if you grant the block universe completely. It does not explain the arrow of time. It makes the problem worse. Relativity is time-symmetric. Einstein's field equations, like Newton's and Maxwell's before them, work identically with the sign of time reversed. Nothing in general relativity distinguishes a contracting universe from an expanding one at the level of the equations. Relativity therefore contributes exactly nothing toward explaining why entropy increases in one direction. And the block universe actively deepens the puzzle, because if the whole of space-time exists as a single fixed structure, then the low entropy state at one end of it was never something the universe evolved into or out of. It sits there as a boundary condition on the entire object. There is a face of the block where entropy is extraordinarily low, and there is a face where it is not. And nothing in the geometry explains why the block is shaped that way rather than symmetrically. You have replaced a question about how the universe started with a question about why the four-dimensional structure has one weird edge, which is the same question wearing different clothes. There is a version of this that people find comforting, and I want to take the comfort away carefully rather than sneer at it. The comforting version says that if all times exist equally, then nothing is really lost, that your childhood is still there in the block, that everyone who has died is still alive at their own coordinates. Physicists say this at funerals. Einstein essentially said it at Bezos. The problem is that the block universe gives you no mechanism by which any of that is experienced. You do not have access to your childhood coordinates. You have access to a physical record stored in the neurons of a brain located at your current coordinates, which correlates with events at earlier coordinates. The reason that record exists, and the reason it points backwards rather than forwards, is thermodynamic. It has nothing to do with relativity. Which means that even in a universe where all times are equally real, the question of why you remember one direction and not the other is untouched, unexplained, and sitting exactly where it was before anybody mentioned Einstein. The expansion of the universe fares no better as a candidate, and this one is worth killing explicitly because it is intuitive and wrong. The universe is expanding, so, the thinking goes, that expansion defines a direction. Except that the expansion is a solution to time-symmetric equations, and a contracting universe is an equally valid solution. And the deeper problem is that expansion, on its own, does not obviously produce entropy increase in the way people assume. If you expand a box of gas slowly and reversibly, its entropy does not change at all. There were serious proposals in the 1960s, including one by Thomas Gold, that the thermodynamic arrow is tied to cosmic expansion and would reverse if the universe began to contract. The proposals did not survive scrutiny. Cosmic expansion is a fact about the universe we live in. It is not a derivation of anything. Relativity fails to explain it. Cosmology in its simple form fails, particle physics fails, and statistical mechanics fails on its own terms. There is one more place people reach for an answer, and it is the one with the most cultural momentum behind it, because it involves the word quantum. There is something else that gets lost when people talk about the arrow of time as if it were one thing, and it is worth slowing down for, because the plurality is itself a clue. Arthur Eddington coined the phrase in the Gifford lectures he gave in 1927, published the following year as The Nature of the Physical World. His definition is precise, and it is worth having exactly. He wrote that we should draw an arrow arbitrarily, and that if as we follow the arrow we find more and more of the random element in the state of the world, then the arrow is pointing toward the future, while if the random element decreases, the arrow points toward the past. He added that this is the only distinction known to physics, and that he would use the phrase time's arrow to express this one-way property of time which has no analogue in space. The only distinction known to physics, from the man who thought the second law held the supreme position among the laws of nature. But since Eddington, physicists have catalogued at least 5 distinct arrows, and they do not obviously have anything to do with one another. There is the thermodynamic arrow, which is entropy increase. There is the psychological arrow, which is the fact that you remember the past and not the future. There is the cosmological arrow, which is the expansion of the universe. There is the quantum measurement arrow, whatever it turns out to be. And there is the radiative arrow, which is the strangest of them and the least discussed outside specialist circles. The radiative arrow is this. Drop a stone into a still pond and you see circular ripples spreading outward from the point of impact. Everyone has seen that. Now consider that Maxwell's equations, which govern the equivalent behaviour for light and radio waves, admit 2 families of solutions. There are retarded solutions in which waves spread outward from a source into the future, and there are advanced solutions in which waves converge inward onto a sink from the future. Both are mathematically valid. Both satisfy the equations exactly, and every single physicist, in every calculation ever performed, throws the advanced solutions away. Not because they are wrong, because we never see them. You have never watched a perfectly circular ripple contract from the edges of a pond converge on a single point and eject a stone upward into someone's hand. You have never seen a radio antenna gather incoming spherical waves from all directions and convert them into a signal. The universe appears to permit only outgoing radiation. John Wheeler and Richard Feynman tried to take the symmetry seriously rather than discarding half of it. Their 2 papers, in Reviews of Modern Physics in 1945, Volume 17, page 157, and again in 1949, Volume 21, page 425, developed what is called absorber theory. Their proposal was to use a time-symmetric combination, half retarded and half advanced, and to show that when you account for the response of all the matter in the universe that will eventually absorb the radiation, the advanced components cancel out, and you recover the outgoing waves we actually observe. It is beautiful, and it very nearly works. It also does exactly what everything else in this story does. The cancellation depends on a condition about absorbers, specifically on the universe being an efficient absorber in the future direction and not in the past direction, which is a cosmological boundary condition, which is the past hypothesis again, wearing a different coat. Now here is the part that ought to bother you more than any individual arrow does. All of them point the same way. There is no known reason for that. The expansion of the universe is a fact about large-scale geometry. Entropy increase is a fact about statistical mechanics. Your ability to remember breakfast is a fact about neurochemistry. Outgoing radiation is a fact about electromagnetism. These are different theories, different scales, different mathematics. Nothing in the formalism connects them. And yet in the entire history of observation, no one has ever found a system in which one of these arrows runs opposite to the others. You can either treat that as an enormous coincidence, or you can conclude that they all descend from a single common source. Almost everyone takes the second option, because the first is absurd. And when you ask what the single common source is, the answer that everyone arrives at, from every direction, is the state of the universe at the beginning, which is the thing nobody can explain. Every road runs into the same wall. The quantum answer comes in 2 versions, one popular and one professional, and they fail in different ways. The popular version says that wave function collapse is irreversible, therefore quantum measurement introduces an arrow of time, therefore the arrow of time comes from observation. You can find this stated confidently in a great many places. The Schrodinger equation is time-symmetric, but collapse is not, and collapse happens whenever a measurement occurs. So there is your asymmetry. The professional version is more careful and more interesting. It says that the relevant process is decoherence, worked out in detail by Wojciech Zurek and others from the 1970s onward. A quantum system does not sit in isolation. It is constantly interacting with an environment of photons, air molecules, thermal vibrations. Those interactions entangle the system with the environment, and the entanglement spreads outward into an enormous number of degrees of freedom that nobody is tracking. The interference terms that make quantum behavior quantum get diluted into that environment. From the point of view of anyone looking at the system alone, the quantum weirdness has vanished. And it has vanished in a way that is practically impossible to undo, because undoing it would require corralling every scattered photon back. That is a genuine account of apparent irreversibility, and it is correct as far as it goes. It also does not explain the arrow of time, and the reason is exactly the same as the reason the H-theorem failed, which should be starting to feel familiar. Decoherence spreads entanglement outward. Entanglement, once spread, is very hard to gather back. But the underlying quantum evolution is unitary, which is the quantum word for reversible. The equations are time-symmetric. Run them backwards, and entanglement gathers instead of spreading, decoherence becomes recoherence, and the mathematics is entirely happy. The only reason decoherence runs in the direction we observe is that the universe began in a state where systems were not already entangled with everything else, a state of extraordinarily low entanglement. There is a name for that in the current literature. It is called the entanglement past hypothesis, and it has been developed in the last few years by Eddie Kemming Chen and collaborators, who are explicit that decoherence produces an arrow only when you feed it a special initial quantum state. Their work is honest about this in a way I appreciate. They are not claiming decoherence solves the problem. They are claiming it relocates the problem to a specific and precisely statable assumption about the initial quantum state of the universe, which is progress of a sort. But it is the same kind of progress as moving a debt from one credit card to another. The interpretation question makes this sharper rather than softer, and this is where the pattern becomes undeniable. Survey the major interpretations of quantum mechanics, and ask each one whether it delivers a fundamental arrow of time. The many worlds interpretation says the wave function never collapses, and the universe evolves unitarily forever. Perfectly time-symmetric. No arrow. Ohmian mechanics says particles have definite positions guided by a pilot wave. The guiding equation is time-symmetric. No arrow. Objective collapse theories like the model proposed by Girardi, Rimini and Weber in 1986 do build in a genuinely irreversible process. Wave functions spontaneously localize at random intervals, and that is a real, fundamental time asymmetric mechanism. This is the one interpretation that delivers an arrow at the level of law rather than initial conditions. But the collapse rate in these models is set so that it is essentially undetectable for single particles, and the resulting asymmetry is nowhere near sufficient to account for the thermodynamic arrow, which is a bulk statistical phenomenon involving numbers of particles with 23 zeros on them. You would still need the low entropy beginning to get eggs to behave. The Copenhagen interpretation says a measurement causes collapse, and declines to say what a measurement is. Notice what all of them share. Every single interpretation, including the ones that fundamentally disagree about whether the wave function is real, whether particles have positions, and whether the universe branches, requires a special low entropy initial condition to reproduce the thermodynamic arrow you observe. They disagree about everything except the thing that actually matters here. The one point of universal agreement in the most contested area of modern physics is that quantum mechanics does not, on its own, tell you why time runs forward. That is the consensus nobody advertises. And it is worth pausing on why nobody advertises it. It is not suppression in any conspiratorial sense, and I want to be careful about this, because the temptation to reach for a cover-up narrative is strong, and the reality is more uncomfortable than a cover-up would be. There is no committee suppressing the arrow of time problem. There are no buried papers. Everything I am telling you is published in mainstream journals by people with tenure. Feynman said it on camera. Penrose put it in a best-selling book. The mechanism is subtler, and it is a mechanism of curriculum, of professional norms, and of what gets counted as a real question. Thermodynamics is taught as a working subject. It has to be, because engineers need it, and it works. Undergraduates learn the second law, they learn the statistical derivation, they learn Boltzmann's formula, and if a student raises a hand and asks why the argument does not run equally well backwards, the honest answer takes 40 minutes, does not appear on the exam, and ends with the lecturer admitting that nobody knows. The efficient move is to say that we assume the universe started in a low entropy state and move on to the next chapter, and the efficient move, repeated across every physics department on Earth for a century, produces graduates who believe the problem was solved in the 1870s. Nobody decided to hide this. It got filed under assumptions, and things filed under assumptions stop being asked about. That is how institutions bury things, not with a lock, but with a category. Which brings us to the assumption itself, and to the man who finally gave it a name in the year 2000, and to the extraordinary fact that naming it clearly made it more obviously indefensible rather than less. David Albert is a philosopher of physics at Columbia University who was trained as a theoretical physicist and who writes about quantum mechanics and thermodynamics with a kind of impatient clarity that a lot of working physicists find annoying. In 2000, Harvard University Press published his book Time and Chance. In it, he gave the assumption a name that stuck. He called it the past hypothesis. The formulation is this: in addition to the dynamical laws, and in addition to the statistical postulate that assigns equal probability to every microscopic state consistent with what you know, you must add a third ingredient. You must postulate that the universe began in a particular macroscopic state of extraordinarily low entropy. You do not argue that it probably did, or that it is likely to have. You postulate it, as an axiom, alongside the laws of motion. Once you add it, everything works. The statistical arguments that ran backwards and predicted nonsense now run correctly, because they are constrained at one end. Your memories become reliable. The fossil record becomes evidence. Ice cubes were previously colder rather than previously spread out. Every inference about the past that you make thousands of times a day without noticing becomes valid, and it becomes valid because of an axiom that was inserted by hand precisely in order to make it valid. Take that in properly, because the circularity is the whole story. We know the past was low entropy because we remember it, and because there are records of it. But our reason for trusting memories and records at all is that the past was low entropy. Remove the postulate, and you cannot bootstrap it back from evidence, because the evidence only counts as evidence if you already have the postulate. Albert's own framing of this is that the past hypothesis is what makes the past knowable, which means it cannot itself be something we learned by looking at the past. Feynman got there decades earlier and said it more brutally. In the fifth of his messenger lectures at Cornell, published as The Character of Physical Law, in a chapter titled The Distinction of Past and Future, he laid out the whole problem and then delivered the verdict. He said it is necessary to add to the physical laws the hypothesis that in the past the universe was more ordered, in the technical sense, than it is today. He noted that the statement is itself lopsided in time, unlike everything else in physics. And then he said that it comes outside the province of what we ordinarily call physical laws. I keep returning to that phrase because of what it concedes. Physics, as a discipline, is in the business of explaining the world with laws. Here is a feature of the world, arguably the most pervasive feature of the world, present in every observation any human being has ever made, and the best available account of it requires a statement that its own author classifies as not a physical law. Hugh Price at Cambridge reframed the question in a way that I think is the cleanest statement of what is actually at stake. His book, Time's Arrow and Archimedes' Point, published by Oxford in 1996, argues that most discussion of the arrow of time is contaminated by our own temporal perspective, that we ask the wrong question because we are standing inside the asymmetry we are trying to explain. Strip that away, he says, and the real question is not why entropy increases. Entropy increases because it is overwhelmingly probable that it should, and that part was never mysterious. The real question is why it was ever low to begin with. Why was it ever low to begin with? That is the whole of it. Everything else is bookkeeping. The critical responses are worth taking seriously rather than waving past. John Earman, a philosopher of physics at Pittsburgh who spent a career on the foundations of general relativity, concluded after examining the past hypothesis in detail that it is not even coherent enough to be false. His objection is technical, and it concerns whether you can define entropy for the universe as a whole, in general relativity, in a way that makes the hypothesis a well-posed statement at all. In a space-time with singularities and no global time slicing, the notion of the entropy of the initial state may simply fail to have a definition. That is not a small problem for something you are proposing to install alongside Newton's laws. Barry Luer and Albert have pushed back in the other direction, arguing that the past hypothesis should be treated as a candidate fundamental law in its own right, part of the best system description of the universe. No more mysterious than the value of the gravitational constant. It is a serious position. It is also, when you look at it directly, a proposal to solve the problem by declaring it solved. We cannot derive the initial condition, therefore we promote the initial condition to the status of a law and stop asking. That may be correct. It is not an explanation. And then there is Maudlin, whose response is the most radical and the one I find hardest to argue with, even though I do not think I believe it. Maudlin's position is that everybody has the logic backwards. The direction of time, he argues, should never have been handed over to entropy for explanation. He takes it as a primitive feature of the world, as basic as the existence of space. And the reason physicists find themselves unable to derive it is that they are trying to derive something fundamental from something derivative. On his view, the passage of time is built into the structure of reality at the ground floor. The laws generate later states from earlier ones in a genuinely directed way, and the increase of entropy is a consequence of that directedness, rather than the source of it. The reason this is hard to dismiss is that it explains why every attempt to derive the arrow from time's symmetric laws has failed for 150 years. Maybe they failed because it cannot be done all along, and the mathematical formalism, which happens to be built out of time's symmetric differential equations, simply does not represent it. The reason it is hard to accept is that it gives up on the project. It says the direction of time is a brute fact that physics should stop trying to explain, which is exactly the move that physics has spent 4 centuries refusing to make about anything else. I do not know which of these is right, neither does anyone else, and the people who have thought hardest about it are the ones most willing to say so. But there is something underneath this argument that almost never gets said in the philosophical literature, and it is the thing that turns this from an abstract dispute into something that should genuinely unsettle you. Consider what a memory physically is. Set aside what it feels like and ask what it is made of. A memory is a physical configuration, a pattern of synaptic strengths in a brain that correlates with an event that happened earlier. Same for a photograph, a fossil, a tree ring, a layer of ice in a Greenland core, a line of text in a ledger. All of them are physical structures in the present whose arrangement carries information about the past. Making one of those structures costs entropy. Rolf Landauer proved this at IBM in 1961 in a paper in the IBM Journal of Research and Development, and I will come back to the details because they matter enormously. But the headline is that recording and erasing information are thermodynamic processes with a minimum unavoidable cost in dissipated heat. Records are not free. They are paid for out of the same entropy budget as everything else, which means the entire evidential basis for believing the past was low entropy consists of physical objects that exist only because the past was low entropy, that cost entropy to produce, and that in principle could be produced by any process capable of paying the same bill. Hold that. I am going to leave it there for now, because it does not become genuinely frightening until you know how big the entropy budget actually is, and where it came from, and what happens to it when it runs out. The number is coming. I have been putting it off, because it is the single least comprehensible quantity in all of physics, and because you need to understand one deeply counterintuitive thing about gravity before it will mean anything at all. First, a correction that will make everything else easier, and which is itself one of the most persistent errors in popular science. Entropy is not disorder. Every textbook analogy about messy bedrooms and shuffled cards has done real damage here, because disorder is a subjective aesthetic judgment, and entropy is a number you can calculate. Arya Ben-Naim, who has written several books trying to kill this analogy, put it well when he observed that interpreting entropy as a measure of disorder has itself caused a great amount of disorder in the literature. What entropy actually counts is microstates. Take a system and specify its large-scale properties: the temperature, the pressure, the overall distribution of matter. That is the macrostate. Now count how many distinct microscopic arrangements of the individual particles would produce that same macrostate. That count, the logarithm of it multiplied by a constant, is the entropy. High entropy means the macrostate is one that can be realized in an enormous number of ways. Low entropy means very few arrangements produce it. The formula that expresses this is carved on Boltzmann's tombstone in the Zentralfriedhof in Vienna. Entropy equals K log W. The K is Boltzmann's constant, which since the redefinition of the International System of Units in 2019 has an exact defined value of 1.3806 for 9 times 10 to the minus 23 joules per Kelvin. The W counts the arrangements. It is worth knowing that Boltzmann never actually wrote the formula in that form. Max Planck did. Boltzmann's tombstone carries Planck's notation. Now here is the part that inverts everything, and it is the single most counterintuitive fact in this entire subject. For ordinary matter with no gravity, spread out and uniform is high entropy. Put a drop of ink in water and it disperses, because there are far more arrangements in which the ink molecules are scattered throughout than arrangements in which they are clumped in one spot. Uniformity is the equilibrium state. That is the intuition everyone has, and for gases in boxes it is correct. Turn gravity on, and the logic reverses completely. Gravity is universally attractive. It has no opposite charge, nothing that cancels it, no screening. Which means that for a system where gravity dominates, a smooth uniform distribution of matter sits nowhere near the equilibrium state. It is unstable, finely balanced, and extraordinarily special. The system can enormously increase the number of available arrangements by clumping. Matter falls together, gravitational potential energy converts into kinetic energy, and then into heat and radiation, structures form, and the entropy goes up. Stars are entropy-generating engines. galaxies are higher entropy than the diffuse gas they formed from, and the highest entropy objects in the universe, by an absurd margin, are black holes. Jacob Bekenstein and Stephen Hawking worked out in the 1970s that a black hole has an entropy proportional to the area of its event horizon, and the numbers that come out of that formula are unlike anything else in physics. A black hole with the mass of the Sun has an entropy of roughly 10 to the 77th in natural units. For comparison, the Sun itself, as a working star made of hot plasma, has an entropy of about 10 to the 58th. Collapsing the Sun into a black hole would increase its entropy by a factor of 10 to the 19th. For perspective, that gap is the difference between the population of a small town and a number vastly larger than every atom in every human body that has ever lived. Which means that when you look up at the early universe, at the cosmic microwave background, at that famously smooth uniform glow, which is the oldest light in existence, and which is uniform in temperature to about 1 part in 100,000, you are not looking at a high entropy equilibrium state. You are looking at the lowest entropy configuration gravity has ever been in. That smoothness is the anomaly. That smoothness is the fuel. Every ordered thing that has ever happened, every star that has ever ignited, every planet that has formed, every organism that has metabolized, every thought you have ever had has been paid for out of the entropy gap between that initial smoothness and the clumped, black hole-dominated state the universe is heading toward. Roger Penrose spent a career on this, and in 1979, in a contribution to a volume marking the centenary of Einstein's birth, he made it quantitative. His paper was titled Singularities and Time Asymmetry, and in it he proposed what is now called the Weyl curvature hypothesis. The Weyl tensor is the part of space-time curvature that describes tidal distortion and gravitational waves. The part that can exist even in empty space, as distinct from the part directly produced by local matter density. Penrose's hypothesis is that at the initial singularity the Weyl curvature was zero or very close to it, meaning space-time began in a maximally smooth gravitational state, while at final singularities inside black holes, the Weyl curvature diverges. That asymmetry, he argued, is the origin of the thermodynamic arrow of time, and it is a condition imposed on the initial state, not derived from any dynamical law. Then he calculated how special that initial state was. The reasoning runs like this. Take all the matter in the observable universe, roughly 10 to the 80th baryons. Ask what its entropy would be if gravity had been allowed to do its worst, if everything had collapsed into black holes rather than remaining smooth. Using the Bekenstein-Hawking formula, you get a total entropy on the order of 10 to the 123rd. The actual initial state had entropy vastly lower than that, and since entropy is the logarithm of the number of available arrangements, the fraction of the available states that correspond to the actual beginning of our universe is 1 over 10 raised to the power of 10 to the 123rd. Sit with the structure of that number rather than the size of it, because the size is not something a human being can hold. It is not 10 to the 123. That would already be a number about 43 orders of magnitude larger than the count of atoms in the observable universe. The 123 is the exponent of the exponent. To write the full number out in ordinary decimal notation, you would need 10 to the 123 zeros. There are only about 10 to the 80th atoms in the observable universe. If you could write 1 0 on every atom in existence, using the entire cosmos as your notepad, you would run out of atoms after 10 to the 80th zeros, and you would still be short by a factor of 10 to the 43rd, which is itself larger than the number of atoms in 100 trillion galaxies. The improbability of the initial state of the universe cannot be written down inside the universe. That is the situation. I should be honest, that the exact figure is contested, and it is contested for reasons that are themselves revealing. Gravitational entropy does not have a universally agreed rigorous definition. The calculation depends on assumptions about whether you imagine all the matter collapsed into a single black hole or many, on how you treat the cosmological horizon, and on whether the Weyl curvature is really the right measure. There are technical papers pointing out that Weyl-based entropy measures can behave non-monotonically in certain spacetimes, which is a problem if you want to use them as an entropy. Penrose's number is an estimate with a large fog around it, but the fog is a fog of orders of magnitude in the exponent of the exponent. Even generous disagreement leaves you with an initial state so improbable that no ordinary probabilistic language survives contact with it. Nobody working in the field disputes the qualitative claim. They dispute the decimal places on a number whose decimal places cannot be written down. For the present state of things, we have much better measurements. In 2010, Chas Egan and Charles Lineweaver at the Australian National University published a paper in the Astrophysical Journal, volume 710, page 1825, titled A Larger Estimate of the Entropy of the Universe. They went through every contribution they could quantify and produced the current best number for the entropy of the observable universe, and it came out at about 3.1 times 10 to the 104th, in units of Boltzmann's constant, with an uncertainty that runs from about 1.4 to about 6 times that. The headline finding was the dominance of black holes. Supermassive black holes at the centres of galaxies contribute more entropy than everything else combined by orders of magnitude, and better data on their number and masses forced the estimate upward by roughly a factor of 30 compared to previous calculations. Egan put it plainly in the press release, saying that when they used the new data on the number and size of supermassive black holes, they found that the entropy of the observable universe is about 30 times larger than previous calculations had suggested. The cosmic microwave background, all that radiation, all that light from the beginning of everything, contributes about 10 to the 88th. It is a rounding error next to the black holes, and the cosmic event horizon itself, the boundary beyond which we cannot see, carries an entropy of about 2.6 times 10 to the 122nd, which dwarfs everything inside it by 18 orders of magnitude. Now put the two numbers side by side. Current entropy of everything we can observe, around 10 to the 104th. Maximum available entropy, if gravity finished the job, around 10 to the 123rd. We are 19 orders of magnitude from the bottom of the well. The universe is roughly 14 billion years into a process of falling, and it has barely started. That gap is your life. Every biological process, every act of memory formation, every thought, is a small local transaction against that 19 order of magnitude difference. You are not experiencing the passage of time in some abstract metaphysical sense. You are a structure that persists by burning through a fuel supply that was laid down before the first star ignited, and the direction you call forward is the direction in which that fuel is being spent. And nobody knows why the tank was full. There is an obvious answer waiting at this point, and it is the answer most cosmologists reach for, and it has a serious problem that Penrose has been pointing at for 40 years, while the field mostly declines to engage. The answer is inflation. In the standard picture, developed by Alan Guth and others from 1980 onward, the very early universe underwent a period of exponential expansion, doubling in size something like 60 times in a fraction of a second. Inflation was invented to solve several problems at once, and one of them is precisely the smoothness. Whatever the universe looked like before inflation, the expansion stretched any irregularity out to scales far larger than anything we can see, leaving behind a patch that is flat and uniform to a fantastic degree. The smoothness of the cosmic microwave background is exactly what inflation predicts. The tiny fluctuations in it, 1 part in 100,000, match the quantum fluctuations inflation says should have been stretched into existence. It is one of the genuine successes of modern cosmology. Penrose's objection is that it does not touch the entropy problem, and that anyone who thinks it does has not counted the states. His argument is this: inflation requires a starting patch that is itself in a very particular condition, small, smooth enough, and dominated by a scalar field sitting in a very specific part of its potential. If you ask how probable such a starting patch is, using the same phase space counting that produced the number in the first place, you find that it is itself fantastically improbable. Inflation does not manufacture low entropy. It takes a low entropy starting point and stretches it. The bill still has to be paid, and inflation pays it by borrowing from an even more improbable predecessor. The complaint appears in The Emperor's New Mind, in The Road to Reality, and in seminars and papers going back 4 decades, and the standard cosmological response is essentially to note the objection and continue. I find that response genuinely strange. Penrose won the Nobel Prize in Physics in 2020 for the singularity theorems, which is to say for proving results about the structure of space-time that underpin the entire field. When that person says your favourite mechanism has a hole in its foundations, the professional norm ought to be a fight, not a footnote. To be fair, there is a fight, and it has been getting more interesting recently. In 2022, Guido D'Amico, Nemanja Kaloper and collaborators published a paper in Physical Review D, Volume 106, Article 103503, arguing that power law inflation can in fact begin from a past null singularity where the Weyl tensor vanishes, which is exactly the condition Penrose's hypothesis demands. If that holds up, inflation is not violating the Weyl curvature hypothesis, but satisfying it, and the arrow of time emerges from a spontaneous breaking of time symmetry at the initial boundary. It is a serious technical response, and it is recent enough that the dust has not settled. Then there are the proposals that give up on explaining the low entropy beginning, and try to explain it away instead. Sean Carroll and Jennifer Chen wrote the most discussed one in 2004, a preprint titled Spontaneous Inflation and the Origin of the Arrow of Time, which was never published in a journal, but which has shaped a great deal of subsequent thinking. Their idea starts from the observation that entropy may have no maximum. If space can always create more space, if the number of available degrees of freedom is unbounded, then there is no equilibrium state to sit in, and the notion of a universe that has finished increasing its entropy is incoherent. In their picture, empty de Sitter space with a small positive vacuum energy, which is roughly what our universe is heading toward, is not stable. It occasionally, over unimaginable timescales, spawns a baby universe through a quantum fluctuation, which then inflates into a region like ours. The process runs in both time directions from any given starting point, producing an infinite multiverse that is statistically time-symmetric overall, in which each individual baby universe has its own local arrow pointing away from its own birth. There is no global arrow of time, and no need for a special initial condition. Because there is no initial condition. There is just an eternal process, and we are inside one of its products. It is a genuinely creative solution, and it has been criticised hard. Hrvoje Nikolic published a comment on it later that same year, disputing the claim about where the minimum entropy surface actually lies. More broadly, the proposal relies on rare fluctuations in a system with infinitely many degrees of freedom, and once you are in that territory, a specific problem shows up that we will get to shortly, and that eats most theories of this shape alive. The most elegant alternative comes from Julian Barbour, who has spent his career arguing that time itself does not exist as a fundamental quantity. In 2014, Barbara Tim Kozlowski and Flavio Mercati published a paper in Physical Review Letters, Volume 113, Article 181101, titled Identification of a Gravitational Arrow of Time. Their opening claim is unusually direct for a physics abstract. They wrote that it is widely believed that special initial conditions must be imposed on any time-symmetric law if its solutions are to exhibit behaviour of any kind that defines an arrow of time, and that they show this is not so. What they did was study a system of gravitating particles with zero total energy and zero total angular momentum, which is what a self-contained universe would have. They then defined a measure of structural complexity for such a system, essentially a measure of how clustered and organised the configuration is. What they found is that generic solutions have a unique moment of minimum complexity, which they named the Janus point after the Roman god who faces both directions. On either side of that point, complexity grows. In both directions, away from the middle. Which means that a typical solution to time-symmetric gravitational laws produces two arrows of time, back to back, pointing away from each other. Any observer inside such a solution, on either branch, would experience a low complexity past and a high complexity future, and would conclude that time flows in the direction of increasing structure. Two populations of observers on opposite sides of the Janus point would each regard the other as living backwards, and neither would be wrong. No special initial condition required. The asymmetry emerges from the dynamics of gravity itself, given nothing but the constraints of being a closed universe. I like this one more than any of the others, and I want to be careful about why, because liking a theory is not evidence for it. What appeals is that it does not smuggle. Every other proposal on this list either assumes the low entropy beginning, or explains it by positing something even more special, or dissolves it into an infinite ensemble where the question stops being well posed. Barber and his collaborators are attempting to derive the asymmetry from time-symmetric ingredients honestly, which is the thing everybody has been trying and failing to do since 1872. Whether it scales up from a toy model of point particles to a real universe with quantum fields and thermodynamics is an open question, and the honest answer is that nobody knows yet. Penrose has his own proposal, and it is the strangest of all of them. Conformal cyclic cosmology, laid out in his 2010 book Cycles of Time, holds that the far future of our universe, after every black hole has evaporated and only massless radiation remains, becomes mathematically indistinguishable from the beginning of a new universe. Without massive particles there are no clocks and no rulers, so scale ceases to have meaning, and the infinitely expanded dead end of one aeon can be conformally rescaled into the hot dense beginning of the next. The low entropy start of our universe is the high entropy end of the previous one, viewed through a change of scale that makes the distinction meaningless. He has looked for evidence. In 2020, Daniel Ann, Krzysztof Meissner, Paul Nurowski and Penrose published a paper in the monthly notices of the Royal Astronomical Society, volume 495, claiming to find what they call Hawking points in the cosmic microwave background, concentrated spots of energy that they interpret as the imprint of supermassive black holes evaporating in the previous aeon. The reception has been sceptical, and I think justifiably so. Dylan Zhao and Douglas Scott at the University of British Columbia reanalysed the claim in 2019 and found that when you compare the claimed features against realistic simulations of a standard cosmology, the significance drops to around 1 sigma. 1 sigma is noise, and underneath all of these attempts sits the option that a certain kind of physicist reaches for when everything else fails, which is to say that the initial condition does not need explaining, because only universes with low entropy beginnings can contain observers, and here we are, observing the anthropic argument. I understand the appeal, and I think it fails. Not because anthropic reasoning is illegitimate in principle, but because in this specific case it makes a prediction, and the prediction is monstrous. Which brings us back to Dr. Schwetz. Before the trap closes, I owe you the promised detail about memory, and 2 corrections about experiments that get badly misreported, because the misreporting is doing real damage to how people think about this. Rolf Landauer was a physicist at IBM's Thomas J. Watson Research Center, and in 1961 he published a paper in the IBM Journal of Research and Development, Volume 5, page 183, titled Irreversibility and Heat Generation in the Computing Process. What he established is now called Landauer's principle, and it is one of the few genuinely deep results connecting information to physics. The principle says that erasing one bit of information necessarily dissipates a minimum amount of heat into the environment, and that minimum is Boltzmann's constant multiplied by the temperature multiplied by the natural logarithm of 2. At room temperature 300 Kelvin, that works out to about 2.9 times 10 to the minus 21 joules per bit. It is a small number, it is not 0, and the fact that it is not 0 is the point. Why does erasure cost anything? Because erasure is logically irreversible. Before erasure, a bit could have been in either of 2 states. After erasure it is in one known state. 2 possibilities have become 1. The number of microstates available to the system has been halved, and since entropy is the logarithm of the count of microstates, the entropy of the memory has gone down. The second law does not permit that for free. The reduction in the memory's entropy must be paid for by an increase somewhere else, and the somewhere else is heat flowing into the surroundings. For 50 years this was a theoretical result that some people doubted. Then in 2012, Antoine Barout and colleagues published a paper in Nature, volume 483, page 187, titled Experimental Verification of Landauer's Principle Linking Information and Thermodynamics. They took a single colloidal particle in an optical trap, shaped like a double well, used the 2 wells as the 2 states of a bit, and performed erasure cycles while measuring the heat dissipated. For slow enough cycles, the measured heat converged on the Landauer bound from above, exactly as predicted. The connection between information and thermodynamics is not a metaphor. It has been measured on a single particle. Now apply it to yourself. Every memory you have is a physical record. Forming it required your brain to do thermodynamic work, dissipating heat, increasing the entropy of your surroundings. Your brain runs at roughly 20 watts, and a meaningful fraction of that is the cost of maintaining and updating the physical structures that constitute your model of the past. You are a recording device, and recording devices run on entropy the same way engines run on fuel. This is why memory points backwards. There is no mystery about it once you see the mechanism. To have a record of an event, the record must correlate with the event, and establishing that correlation requires an interaction that increases total entropy. Since entropy increases toward what we call the future, records can only exist of what we call the past. A record of the future would require a correlation established by an interaction whose entropy cost was paid in the wrong direction, and there is no fuel flowing that way. The asymmetry of memory is not a psychological fact. It is a thermodynamic one, which means your sense that time flows, the felt experience of the present moment sliding forward, leaving a trail of remembered events behind it and nothing at all ahead, is a report generated by a physical system that can only accumulate correlations in one direction, because it is sitting on the slope of a 19 order of magnitude entropy gradient laid down before the first star. You are not watching time pass. You are the process by which some of the universe's remaining order is converted into a record of the order it used to have. Now the corrections. Because there is a genre of headline that undermines all of this, and it needs dismantling. In 2019, a group led by Gordy Lesovic published a paper in Scientific Reports, Volume 9, Article 4396, titled Arrow of Time and its Reversal on the IBM Quantum Computer. The headlines that followed said that physicists had reversed time. What they actually did was implement a quantum algorithm on IBM's publicly accessible quantum processors that takes a known, deliberately prepared quantum state, applies a complex conjugation operation, and returns the system to its starting configuration. With 2 qubits, it worked about 85% of the time. With 3 qubits, about 50%, the drop caused by hardware imperfections. That is a real and useful piece of work about quantum error correction and the difficulty of state reversal. It is not time reversal in any sense relevant to this story. The reversal required an external agent who already knew the initial state, applied a precisely designed operation from outside, and expended energy doing so. The entropy of the universe went up during the procedure, not down. Rewinding a recording is not reversing time, and the machine doing the rewinding had to pay for the privilege. The same applies to spin echo, which is older and cleaner, and which every graduate student in nuclear magnetic resonance learns. Erwin Hahn published it in Physical Review in 1950, Volume 80, page 580. You put a sample of nuclear spins in a magnetic field, they start out aligned, and then they dephase because each spin sits in a slightly different local field and precesses at a slightly different rate. Within milliseconds, the coherent signal has vanished into apparent randomness. Then you apply a carefully timed radio pulse that flips every spin, and the dephasing runs backwards, and the signal reappears out of nowhere as an echo. It looks exactly like entropy spontaneously decreasing. It is not, because the information was never actually lost, only spread into correlations among the spins, and the external pulse that inverted them was applied by an experimenter who dissipated energy to generate it. In 2019, Kaunan, Mikade and colleagues published a paper in Nature Communications, Volume 10, Article 2456, showing something more interesting. Using 2 nuclear spins prepared with quantum correlations between them and held at different effective temperatures, they observed heat flowing spontaneously from the cold spin to the hot one. Genuinely uphill, genuinely spontaneous, no external intervention during the flow. That sounds like a violation of the second law, and it is not one. What powers the uphill flow is the consumption of the pre-existing quantum correlations between the 2 spins. As heat moves the wrong way, the mutual information between the spins is destroyed, and the total accounting comes out fine. The lesson is not that thermodynamics is wrong. The lesson is that the familiar rule about heat flowing from hot to cold contains a hidden assumption, namely that the 2 systems started uncorrelated, and when that assumption fails, the direction flips, which is again exactly the shape of this entire problem. The arrow depends on initial conditions, and when you change the initial conditions, the arrow changes with it. And then there is the result that I still find the most quietly disturbing, because it is the second law being caught in the act. In 1993, Denis Evans, Ezekiel Cohen and Gary Morris published a paper in Physical Review Letters, Volume 71, page 2401, establishing what is now called the fluctuation theorem. It gives you a precise expression for the ratio of the probability that entropy increases by a given amount to the probability that it decreases by the same amount over a given time in a given system. For macroscopic systems over macroscopic times, the ratio is so overwhelmingly lopsided that entropy decrease is impossible for practical purposes. For small systems over short times, it is not. In 2002, Genmiel Wang, Edith Sevick and colleagues at the Australian National University tested it. Their paper, is in Physical Review Letters, Volume 89, Article 050601, and the title says exactly what it did. Experimental demonstration of violations of the second law of thermodynamics for small systems and short time scales. They dragged a single micron-sized latex bead through water using an optical trap and measured the entropy production continuously. Over intervals up to about 2 seconds, they measured stretches in which the entropy of the system went down. They did not infer it statistically, they measured it. The second law of thermodynamics has been observed being violated in a laboratory repeatedly at micron scales over intervals of a couple of seconds. It is a bet that gets better the more particles you are betting on, which means the thing standing between you and a universe where the past is unreliable is a probability rather than a law of nature, and the probability is enormous, but probabilities work on both ends of a timeline, and there is one specific way of setting up the universe in which the odds come out very badly indeed. Boltzmann proposed that setup in 1895. It took another century for anyone to work out what it costs. Take the Schetz proposal seriously for a moment. The universe is at thermal equilibrium, eternally, and every ordered thing is a fluctuation. Our entire observed cosmos, all the galaxies and all the structure and all of recorded history, is a statistical accident on the slope of a very large deviation from equilibrium. Now ask a question that Boltzmann never asked, and that nobody asked clearly until the 1990s. What size of fluctuation is required to produce what you are currently experiencing? The answer is that you do not need a whole universe. You need a brain. Whatever you are experiencing right now, this room, these words, your memories of this morning, is a state of your brain. If a fluctuation can produce a 14 billion-year-old universe containing a brain, it can also produce, far more cheaply, just the brain, complete with a full set of false memories, hallucinating a body and a room and a history, and then dissolving back into the equilibrium it came from a moment later. And cheaply is doing enormous work in that sentence. The probability of a fluctuation is exponentially suppressed by the size of the entropy decrease required. A brain requires a decrease in entropy of some magnitude. A universe containing that brain, along with 100 billion galaxies and 14 billion years of low entropy history, requires a decrease that is larger by a factor, with an enormous number of digits in it. Since the suppression is exponential in that difference, the ratio of lone brains to complete universes in an eternal equilibrium is large in the way that Penrose's number is large, which means, if the fluctuation picture is correct, that the overwhelming majority of entities in the universe having your exact present experience are momentary assemblies with fabricated memories. Floating in equilibrium, lasting a few seconds, surrounded by nothing, they are called Boltzmann brains, which is unfair to Boltzmann and to Schwetz, neither of whom drew the conclusion. But the name has stuck. For most of the 20th century, this was regarded as a curiosity, a reason to reject the eternal equilibrium picture and move on. Then cosmology made it urgent, and it made it urgent by accident. In 1998, 2 independent teams studying distant supernovae found that the expansion of the universe is accelerating, which implies a positive cosmological constant, a vacuum energy that does not dilute as space expands. That result won the Nobel Prize in 2011, and it is about as solid as observational cosmology gets, and it means that the far future of our universe is de Sitter space, an eternally expanding vacuum with a fixed horizon and a fixed non-zero temperature. A space with a fixed non-zero temperature that lasts forever is a thermal system with infinite time available, which is precisely the setup Schwetz described. Fluctuations will happen. Given eternity, every fluctuation compatible with the physics will happen infinitely many times, including brains. Lisa Dyson, Matthew Kleban and Leonard Susskind wrote the paper that made the field pay attention in 2002. It appeared in the Journal of High Energy Physics, and its title is Not Subtle: Disturbing Implications of a Cosmological Constant. Their argument is that a positive cosmological constant leads inevitably to very deep paradoxes which seem to require major revisions of the usual assumptions. Andreas Albrecht and Lorenzo Sorbo followed in 2004 with a paper in Physical Review D asking whether the universe can afford inflation, arriving at the same difficulty from a different direction. The problem is not that Boltzmann brains are weird, the problem is what their existence does to your reasoning. Sean Carroll laid this out in a paper called Why Boltzmann Brains Are Bad, posted in 2017 and published in a Philosophy of Science collection. His conclusion is that theories predicting a dominance of Boltzmann brains are, in his phrase, cognitively unstable. They cannot simultaneously be true and justifiably believed. Follow the logic, and it closes like a trap. You believe in the fluctuation cosmology because of evidence. The evidence consists of astronomical observations, laboratory results, textbooks, your training, your memories of reading and checking things. All of that is a physical record stored in your brain and in the world around you. But if the theory is true, then the overwhelming probability is that you are a fluctuation, and every one of those records is fabricated noise that happen to assemble into a coherent-looking pattern. Your memory of checking the calculation did not correspond to any calculation. The paper you think you read was never written. The universe you think you observed does not exist beyond the boundary of the fluctuation, which is roughly the size of your skull. Therefore, the evidence for the theory is worthless, because the theory says the evidence is almost certainly fake. A theory that undermines the grounds for believing it ends up somewhere worse than refuted. It becomes a theory that, if you accept it, gives you a decisive reason to stop accepting it, and there is no stable position from which to hold it. There are responses. Don Page published a paper in 2017 arguing that ordinary Bayesian reasoning is enough to reject Boltzmann brain-dominated theories without needing to invoke cognitive instability as a special principle. Essentially, that such theories make terrible predictions about what you should observe and can be rejected on normal empirical grounds. Others argue about whether de Sitter space genuinely fluctuates dynamically, or whether the fluctuations are an artifact of a bad calculation, and there is a serious line of work by Body, Carroll and Pollack suggesting that a quantum system sitting in a stationary state does not actually fluctuate at all in the required sense, because nothing is happening in it. That last one may well be the resolution. I hope it is, but look at what it means. The best current defense against the conclusion that you are a hallucinating fragment with no past is a technical claim about whether stationary quantum states in de Sitter space undergo genuine dynamical fluctuations. That is what the reliability of your memory currently rests on in the literature. It does not rest on anything you could check, or on anything anyone could check. It rests on a contested question about the behaviour of the quantum vacuum in the infinite future. And underneath every one of these arguments, holding all of them up, sits the same postulate that Feynman said comes from outside the province of physical laws. The past hypothesis is what rules out the fluctuation. It is the thing that says no, the universe really did begin in a state of extraordinarily low entropy, your memories really do correspond to events, the record is real. We cannot derive it. We cannot test it, because every test uses records whose validity it underwrites. We assume it because without it nothing makes sense, and then we build the whole of cosmology, the whole of thermodynamics, the whole of history, and the entire content of your own biography on top of it. Boltzmann never got to see any of this worked out. And the reason it became urgent rather than remaining a curiosity has to do with where the universe is actually going, which is worth being concrete about because the abstraction hides how strange the far future is. Fred Adams and Gregory Laughlin laid out the standard picture in a long review in Reviews of Modern Physics in 1997, and the broad shape has held up. Star formation continues for perhaps another 100 trillion years, until the gas runs out. After that, the last dim red dwarfs burn out, and the universe becomes a collection of stellar remnants. White dwarfs cooling toward absolute zero, neutron stars, and black holes. Then, the black holes take over, because black holes are where the entropy is, and black holes evaporate. Hawking showed in 1974 that a black hole radiates thermally and slowly loses mass, and the evaporation time scales as the cube of the mass. For a black hole with the mass of the Sun, the estimate is on the order of 10 to the 67th years. For the supermassive black holes at the centres of galaxies, millions to billions of solar masses, the timescale climbs to somewhere in the region of 10 to the 9th years and beyond. Try to place those numbers against anything human, and the exercise fails immediately. Which is the point. The universe is about 14 billion years old. Written out, that is a 1 followed by 10 zeros. Roughly, 10 to the 67th years is a 1 followed by 67 zeros. The ratio between the current age of everything and the evaporation of a single stellar mass black hole is larger than the ratio between 1 second and the entire history of the cosmos, raised to a power. We are, in the most literal possible sense, in the first instant. And after the last black hole has evaporated, there is a very long stretch of nothing much, in which the expanding vacuum sits at a tiny fixed temperature set by the cosmological constant, and the only events are fluctuations. That is the state Schwetz was describing. It has stopped being a hypothetical. It is where current cosmology says we are going, and it is the reason the Boltzmann brain problem stopped being a curiosity and became a technical crisis in the 2000s. The eternal equilibrium at the end of time is the projected future of the actual universe, and if fluctuations happen in it, then almost every observer who will ever exist has already been accounted for, and the ordinary ones like you are a vanishing minority at the very beginning. Boltzmann had none of this. He had a letter to nature, an assistant's idea, and 11 more years. In the late summer of 1906, Boltzmann took his family on holiday to Duino, a village on the Adriatic coast near Trieste. He was 62. He had been in poor health for years, suffering from severe headaches, worsening eyesight, and episodes of what the medical language of the time called neurasthenia. He had recently returned from a lecture tour in California that had gone badly. He had asked to be relieved of some of his teaching. On the 5th of September, while his wife Henriette and his daughter Elsa were swimming in the sea, Boltzmann took his own life in the room where they were staying. Elsa found him. He left nothing behind explaining it. There is a story that gets told about this, and I want to correct it, because it has become one of the most repeated pieces of misinformation in the history of science, and because the true version is sadder and more interesting. The story says that Boltzmann was driven to his death by the refusal of the scientific establishment to accept atoms, and that he died just before the vindication, never knowing he had been right. It is a good story. It is not accurate. Einstein's paper on Brownian motion, which explained the jittering of pollen grains in water in terms of collisions with individual molecules, and which effectively settled the atomic question theoretically, was published in 1905. Jean Perron's experiments confirming it in detail came in 1908. Boltzmann died between those dates, in a period when atomism was already ascendant, and the energeticist opposition was collapsing. Ostwald himself conceded the reality of atoms in 1909. Boltzmann was not a man who died unrecognised. He had been a professor at Vienna, Munich, Graz and Leipzig. He had been elected to academies across Europe, and his work was known. Carlo Cercignani, whose 1998 biography as the most careful treatment, returns something close to an open verdict, attributing the death to depression and deteriorating physical health rather than to any single intellectual defeat. Some later writers have suggested that if he were assessed today, the diagnosis would likely be a mood disorder with onset in middle age. Historians warn, correctly, against confident retrospective diagnosis of someone dead for over a century. What I find harder to look at is the other thing he was carrying. Boltzmann spent 30 years trying to derive the direction of time from mechanics. He did not manage it. Loschmidt showed him in 1876 that the derivation could not work in principle. Zermelo showed him in 1896 that the conclusion contradicted a theorem. He conceded publicly in print that the second law was statistical rather than absolute, which meant conceding that his life's central project had produced something weaker than what he set out to prove. And in 1895 he put into print, second hand. On behalf of an assistant whose first name barely survives in the record, the only alternative anybody could think of, which was that the direction of time is a local accident inside a dead and eternal universe. He also, in his more careful writing, worked out the consequence of that alternative. He noted that in such a universe, a small fluctuation is vastly more probable than a large one. He was close enough to the Boltzmann brain problem that his name got attached to it a century later. He was right about atoms. He was right that entropy counts microstates. He was right that the second law is statistical. And he was right in a way nobody wanted, that if you take the fluctuation picture seriously, it eats the ground you are standing on. What he could not do, what nobody since has done, is explain why the universe started where it started. The tombstone in the Zentralfriedhof carries the formula. Entropy equals K log W. The equation is correct. It is one of the most important in physics, and it does not contain a direction. You can run it forward. You can run it backward. It counts arrangements, and counting is symmetric. I want to bring this back to where you are sitting. Everything about your experience of being a person is downstream of the unexplained condition at the beginning. The connection is mechanical and traceable through a chain that has no gaps in it. The universe began in a gravitationally smooth state whose improbability cannot be written down inside this universe. That smoothness was the fuel. Gravity pulled matter together and the entropy went up, and the difference between where entropy started and where it is going, currently around 19 orders of magnitude, powers every ordered process there has ever been. Stars burn because of it. Chemistry runs because of it. Your cells maintain themselves against decay because of it. Your brain records the present into memory because recording costs entropy, and there is entropy available to spend. That is why you remember the past and not the future. There is no other reason. The equations do not distinguish. The direction you call forward is the direction in which the fuel is being burned, and you have never had access to any other definition of forward. And you cannot check it. This is the part I have not been able to put down since I started reading for this. Every piece of evidence you have about the past is a physical record in the present. And every physical record exists only because the entropy gradient allowed it to be written. And the reason to trust that the gradient runs the way you think it does is a hypothesis that has to be assumed rather than derived. There is no independent access. There is no external vantage. You cannot step outside the arrow and verify that it points where you think, because the act of verifying is itself a process that runs along it. Feynman said it comes from outside the province of physical laws. Albert named it and showed it has to be assumed. Price asked why it was ever low to begin with and got no answer. Penrose calculated the improbability and got a number that will not fit inside creation. Barber thinks the asymmetry falls out of gravity if you set the problem up right. Maudlin thinks the whole enterprise is backwards and the arrow was fundamental all along. Carroll thinks the alternatives eat themselves. None of them agree. All of them are working on it. And every single one of them is doing that work using memories, notes, papers, and data whose reliability depends entirely on the answer they are trying to find. Right now, as you listen to this, the entropy of your immediate surroundings is increasing. Heat is leaving your body into the air. The neurons holding your attention on this sentence are dissipating energy to maintain a pattern that correlates with the sentence before it. That dissipation is the only thing distinguishing the version of you that heard the last sentence from the version that will hear the next one. It is what makes them different moments rather than the same moment. You are not moving through time. You are a slow, structured discharge of a gradient established 14 billion years ago by a condition that physics has to assume because it cannot explain it, and the sensation of the present moment advancing is what that discharge feels like from the inside. When the gradient is gone, and it will be gone, there is no later. It will not even be darkness, because darkness is a state something can be in, and there will be nothing left to be in it. No processes, no records, no differences between one configuration and the next, and therefore no way for anything to be after anything else. Time does not stop at the end of the universe. It stops having a direction, which turns out to be the same thing as not existing. Boltzmann's formula on the tombstone is still correct. It always was. It counts the number of ways the world could be arranged, and it does not care in which order they come. Somewhere in the first instance of everything there was a configuration so specific that the number describing its rarity cannot be written in this universe, and every moment you have ever experienced. Every face you can picture, everything you are sure happened to you, is a downstream consequence of that one unexplained arrangement. Nobody put it there, nobody knows why it was there, and the only evidence that it ever was there is the memory of it, written in matter, paid for in heat, by a process that could not have gone the other way,